Hello, friend. Welcome back to Night Whisper Science. I am Neil Tyson, and tonight I will be your guide for a very special journey in our series, Whispers from the Milky Way. We are going to venture into the deepest, quietest corners of our cosmos, into the soft, dark clouds that hang like velvet curtains between the stars. These are the stellar nurseries, the cosmic cradles where new suns are born. As you settle in, letting your body grow heavy and your mind become still, allow the story of creation to become your own story of rest. The birth of a star is not a sudden, violent explosion. It is a slow, patient, and magnificent gathering, a gentle collapse over millions of years. Much like the way you now feel yourself sinking softly into a state of deep and peaceful sleep. Let the universe's oldest lullaby, the gentle pull of gravity, soothe you. Let the swirling dust of a nebula be like your own thoughts, slowly settling as your eyelids grow heavy. There is nothing for you to do now but breathe and listen as we explore 20 things you never knew about starbirth. Our first secret of the cosmos is a comforting one. Stars are not born alone. In the vast, lonely expanse of space, birth is a communal affair. Imagine looking up at the night sky, at the countless pinpricks of light. We see them as solitary points, isolated travelers on an endless sea. But this is just a snapshot in time. If we could rewind the cosmic clock, we would see that nearly every star, including our own sun, began its life as part of a grand and bustling family. They are born together in what we call open clusters, all awakening within the same billowy, ethereal cloud of gas and dust. Picture in your mind's eye a place like the Great Orion Nebula, a celestial masterpiece you can glimpse even without a telescope as a fuzzy patch in Orion's sword. It is not just a pretty cloud, it is a metropolis of starbirth. Within its swirling folds of magenta, violet, and deep celestial blue, thousands upon thousands of stars are coming into being at this very moment. These are not quiet, orderly births. It is a vibrant, crowded nursery filled with the radiant light of its newest, most massive children. These young, hot stars illuminate the surrounding gas, causing it to glow with breathtaking color, like a cosmic lantern lit from within. Inside this glowing cocoon, gravity is the great convener. It gently, patiently coaxes particles of dust and molecules of hydrogen gas to drift closer to one another. Over immense timescales, denser pockets begin to form, little knots in the fabric of the nebula. These knots are the seeds, and as they grow, their gravitational pull increases, drawing in more and more material from their surroundings. 1,000 of these seeds, 100,000, can all be forming at once within the same cloud. They are siblings, forged from the very same elemental material, bound together by their shared origin. For a time, these stellar siblings travel together through the galaxy. An open cluster, when it is young, is a spectacular sight, a swarm of brilliant blue and white jewels loosely held by gravity's embrace. The Pleiades, or the Seven Sisters, is a beautiful example you can see in the winter sky. It is a family of young stars, only about 100 million years old, still traveling together through space, their light intertwined. But this family reunion does not last forever. The universe is a dynamic place. As the cluster orbits the center of the Milky Way, it feels the gravitational tides of the galaxy itself. Encounters with other massive clouds can perturb their gentle dance, and the stars themselves, in their own orbits, begin to drift apart. One by one, over hundreds of millions of years, the siblings wander off on their own paths. Like seeds scattered from a milkweed pod, they disperse into the vastness of the galaxy, their shared history forgotten to only the most patient cosmic detectives. Astronomers can trace these family ties. By carefully measuring a star's velocity, its trajectory through space, and its chemical composition, its unique elemental fingerprint, we can identify stars that were born together, even if they are now separated by thousands of light years. We have found many of our sun's long-lost siblings scattered across the galaxy. It gives one a profound sense of connection to know that our own star, the source of all our light and warmth, began its life in the company of thousands of others in a brilliant cosmic nursery long, long ago. So as you drift now, feel that sense of community, of a shared beginning. You are not alone in this vast universe. You are part of a cosmic family, drifting peacefully through the quiet dark. Now, let us venture deeper into this stellar nursery. It is easy to imagine these clouds as serene and placid, like cosmic fog banks hanging motionless in the void. But this brings us to our second secret. The engines of creation are driven by chaos. Star-forming clouds are not still. They are churning, seething cauldrons of supersonic turbulence. The gas within them moves in whirls and eddies at speeds faster than the speed of sound in that medium. It is a silent cosmic storm, a dance of unimaginable scale and power. And it is this very turbulence that sets the stage for birth. For a star to form, a part of the cloud must collapse under its own gravity. But the cloud has its own internal pressure, a warmth that pushes outward and resists this collapse. The turbulence acts as a cosmic sculptor, creating waves of pressure that ripple through the gas. Imagine silent thunderclaps, shock waves of compressed material propagating through the nebula. Where these waves intersect and collide, the gas becomes squeezed into incredibly dense filaments and clumps. These compressed pockets are where gravity's gentle pull can finally overwhelm the outward push of pressure. The turbulence creates the very seeds from which stars will grow. What powers this immense chaotic dance? The triggers are often galactic in scale. A primary cause is the death of a previous generation of massive stars. When a star, many times the mass of our Sun, reaches the end of its life, it explodes in a supernova. This is the most powerful explosion the universe knows. It blasts a shockwave of energy and heavy elements out into space at tremendous speeds. When this shockwave plows into a nearby molecular cloud, it acts like a giant piston, compressing the gas and initiating a new wave of star formation. The death of one star becomes the catalyst for the birth of thousands more. It is the universe's ultimate act of renewal, a cycle of life and death playing out over eons. Stellar winds from large young stars already forming within the cloud can also stir the pot, creating bubbles and shells of compressed gas. Even the gentle, sweeping spiral arms of our own Milky Way galaxy are part of this process. The spiral arms are not solid structures, but rather density waves, areas where stars and gas are temporarily crowded together as they orbit the galactic center. As a molecular cloud passes through one of these dense arms, it gets squeezed, just as a sponge is squeezed in your hand. This galactic-scale compression can be enough to push regions of the cloud over the edge, triggering their collapse into new clusters of stars. So the beautiful spiral shape of our galaxy is not just for show. It is an integral part of its creative engine. The chaos of turbulence, the echo of a distant supernova, the gentle squeeze of a spiral arm, these are the forces that awaken the sleeping giants of the cosmos and begin the slow, inexorable process of creating a new sun. It is a reminder that even from chaos, order and light can emerge. Just as your mind, perhaps filled with the turbulent thoughts of the day, can now find a point of stillness, a dense core of calm from which peaceful dreams can form. As these dense cores of gas begin to collapse, they face a fundamental problem, a challenge of cosmic physics. As the material falls inward, any tiny amount of initial rotation it possesses is amplified, just as an ice skater spins faster when she pulls her arms in. This is the law of conservation of angular momentum. Without some way to slow down, the forming protostar would spin itself into oblivion, flinging all of its material back out into space before it could ever become a true star. It needs a break. And this brings us to our third secret. The universe provides an invisible set of rains, a cosmic midwife in the form of magnetic fields. We think of space as empty, but it is threaded with vast, weak magnetic fields. When a molecular cloud forms, it gathers and concentrates these fields along with the gas and dust. They are frozen into the material, moving with it as it swirls and churns. You can visualize these fields as glowing, ethereal lines of force, weaving through the dark, dense cloud like threads in a cosmic tapestry. They are invisible, but their influence is profound. These magnetic fields play a dual role. Initially, they can act as a support structure, helping the cloud to resist the pull of gravity. The charged particles within the gas cannot easily cross the magnetic field lines, so the field provides an outward pressure, a magnetic scaffolding that can prevent a premature collapse. But once a core becomes dense enough for gravity to truly take over, the role of the magnetic field changes. It becomes a crucial regulator of the birth process. As the core collapses and spins faster and faster, it twists the magnetic field lines that thread through it. This twisting creates a tension that propagates outward along the field lines into the surrounding slower rotating cloud. This tension acts like a magnetic brake. It transfers the rotational energy, the angular momentum, from the rapidly spinning core out into the much larger, more diffuse envelope of gas. It is an incredibly elegant solution. We think of space as empty, but it is threaded with vast, weak magnetic fields. When a molecular cloud forms, it gathers and concentrates these fields along with the gas and dust. They are frozen into the material, moving with it as it swirls and churns. You can visualize these fields as glowing, ethereal lines of force, weaving through the dark, dense cloud like threads in a cosmic tapestry. They are invisible, but their influence is profound. These magnetic fields play a dual role. Initially, they can act as a support structure, helping the cloud to resist the pull of gravity. The charged particles within the gas cannot easily cross the magnetic field lines, so the field provides an outward pressure, a magnetic scaffolding that can prevent a premature collapse. But once a core becomes dense enough for gravity to truly take over, the role of the magnetic field changes. It becomes a crucial regulator of the birth process. As the core collapses and spins faster and faster, it twists the magnetic field lines that thread through it. This twisting creates a tension that propagates outward along the field lines into the surrounding, slower rotating cloud. This tension acts like a magnetic brake. It transfers the rotational energy, the angular momentum, from the rapidly spinning core out into the much larger, more diffuse envelope of gas. It is an incredibly elegant solution. The protostar is allowed to shed its excess spin, funneling it away through these magnetic channels. This allows more and more material to settle down onto the growing star. The magnetic field also acts as a cosmic funnel. It guides the infalling gas and dust, which are often slightly charged, along its field lines, directing a steady stream of material onto the protostar's equator, where it forms a swirling, flattened structure known as an accretion disk. It is from this disk that the star will continue to feed and grow. This silent, invisible force is the choreographer of the final stages of stellar birth, ensuring that the dance of gravity does not end in a chaotic spin, but in the stable, graceful formation of a new sun. It is a force of gentle guidance and control, a slow, steady cosmic rhythm that brings order to the collapse. Let yourself feel that same sense of gentle guidance, a force that slows the spinning of your thoughts, allowing your mind to settle into a state of deep, calm equilibrium. The process of a protostar gathering mass from its surrounding disk is not always a smooth and steady affair. We often imagine it as a constant, gentle rain of material, but the reality is far more dramatic and episodic. This leads us to our fourth secret. A protostar experiences incredible growth spurts, feasting on its parental disk in great, sudden gulps. These events are so dramatic that they have their own classification, FU Orionis objects, named after the first star observed to behave this way. For years, or even centuries, a young protostar might glow with a relatively steady, dim light, slowly sipping material from the inner edge of its accretion disk. But the disk itself is not perfectly smooth. It is lumpy and unstable. Gravitational instabilities can cause large clumps of gas and dust to form within the disk, thousands of times more massive than our own planet. These clumps slowly spiral inward, migrating closer and closer to the young star. When one of these massive clumps finally reaches the inner edge of the disk, it gets torn apart by the star's gravity and rapidly dumped onto the protostar surface. The effect is astonishing. The protostar undergoes a celestial feast. This sudden influx of material creates a tremendous amount of heat and light. In a matter of months or even just weeks, the young star can increase in brightness by a factor of 100 or even 1,000. An object that was previously visible only to powerful telescopes might suddenly become bright enough to be seen with binoculars. It is a cosmic flare-up, a growth spurt of epic proportions. The star is not just brighter, it is fundamentally changed. The surface temperature soars, and a powerful wind is driven off the star, pushing material away. But this feast cannot last forever. After a few decades, or perhaps a century, the outburst subsides. The rate of accretion drops back down to its previous slower pace, and the star fades back to its former dimness, quietly digesting its massive meal. Astronomers now believe that most, if not all, low-mass stars like our Sun may go through several of these FU Orionis outbursts during their formation. This means that the majority of a star's final mass is not gathered slowly and steadily, but in these brief, violent, and incredibly important episodes. It is a cycle of feeding and rest, a rhythm of dramatic change followed by long periods of quiet growth. Much like the rhythm of your own breath, an active inhale followed by a passive, restful exhale. Feel that rhythm now, a cycle of energy and release, activity and calm, as you sink deeper and deeper into a state of peaceful repose. As the young protostar furiously feeds from its accretion disk, it encounters another problem. Not all of the infalling material can be gracefully accepted. Much like a messy eater, the star can't consume everything at once. This cosmic indigestion has spectacular consequences, leading to our fifth secret. Newborn stars create magnificent jets of matter that blast out into space, acting as cosmic pressure release valves. These are known as bipolar jets, and they are one of the most beautiful and energetic signposts of starbirth. Imagine the protostar at the center of its spinning disk of gas and dust. As material spirals inward, the powerful, tangled magnetic fields we spoke of earlier are wound up like a twisted rubber band. This immense magnetic tension creates a tightly focused columnated structure above the star's north and south poles. This structure acts like the barrel of a cosmic cannon. As material gets too close to the star, a fraction of it is caught up in this magnetic tower and violently ejected away from the star at incredible speeds, hundreds of kilometers per second. Two brilliant, narrow beams of superheated gas erupt from the poles, traveling in opposite directions out into the surrounding nebula. These jets are cosmic works of art. They are not continuous, steady streams, but are often clumpy and knotted, pulsing with energy as the accretion onto the star ebbs and flows. As these jets, moving faster than a speeding bullet, slam into the slower-moving gas of the parent cloud, they create luminous, glowing patches called Herbig-Haro objects. These are shock fronts, where the kinetic energy of the jet is converted into light. They can look like delicate, glowing arcs, intricate knots, or vast, ethereal bow shocks, like the wake of a boat moving through water. Their colors can tell us about the chemistry of the jet and the cloud it is hitting. They are like celestial fireworks, announcing the presence of a newborn star still hidden deep within its dusty cocoon. These jets serve a vital purpose. They carry away excess angular momentum from the accretion disk, which, like the magnetic braking we discussed, helps more material to fall onto the star. They also act as cosmic bulldozers. Over thousands of years, they carve out vast cavities in the surrounding molecular cloud. They are the star's first act of shaping its environment, blowing away the very material from which it was born. In time, these jets will help to clear the dusty veil, allowing the star's light to finally shine through, revealing the newly formed sun to the universe. Visualize these two silent, brilliant beams of light erupting from the heart of a dark, spinning disk. Imagine the silent power and grace of these cosmic fountains, a perfectly symmetric and beautiful release of energy, clearing a space for the new life at its center. Not every collapsing cloud core has the destiny to become a brilliant, shining star like our sun. Sometimes the ambition of gravity falls just a little short. This brings us to the boundary between stars and planets, and to our sixth secret, the existence of brown dwarfs, the universe's failed stars. These are objects more massive than a planet, but not quite massive enough to be a star. They are the universe's embers, glowing faintly in the vast cosmic dark. The definition of a star is quite specific. It must be massive enough to create the temperatures and pressures in its core, around 10 million degrees Celsius, needed to ignite the sustained nuclear fusion of hydrogen into helium. This is the process that powers stars for billions of years and makes them shine. To reach this critical threshold, an object needs to have a mass of about 80 times the mass of our own Jupiter. If a collapsing core of gas has less mass than this, it will never get hot enough to begin this process. It will become a brown dwarf. They are born in the same way as stars, from the gravitational collapse of a dense cloud core. For a while, their story is the same. They gather mass, they heat up, they form an accretion disk. Gravity squeezes them, and their internal temperatures rise. They do become hot enough to ignite a different, less efficient kind of nuclear fusion, the fusion of deuterium, a heavy isotope of hydrogen. This provides a brief spark of internal energy, but the deuterium fuel is scarce and runs out quickly. After that, the brown dwarf has no internal energy source. It has failed to ignite the true, lasting fire of a star. For the rest of its long existence, a brown dwarf simply cools down. It glows not from nuclear fusion, but from the leftover heat of its formation, the thermal energy from its initial gravitational collapse. It radiates this heat away into space, mostly in the infrared part of the spectrum. To our eyes, a brown dwarf would be nearly invisible. But with infrared telescopes, we can see their faint, deep magenta or reddish glow. They are like celestial coals that were pulled from the fire before they could truly catch a light. Their atmospheres are complex and fascinating, filled with clouds of molten iron droplets and exotic silicate dust. They are a bridge between the giant gas planets like Jupiter and the smallest, coolest red dwarf stars. They remind us that nature doesn't always deal in absolutes. There are beautiful, fascinating objects that exist in the twilight zones, on the boundaries of our neat classifications. So imagine now one of these lonely, warm embers, a deep, gentle, radiating heat in the vast cold of space. It is not a brilliant beacon, but a soft, subtle glow, a quiet presence holding its own unique place in the cosmic tapestry. From the smallest, failed stars, we now turn our attention to the titans of the cosmos, the true kings and queens of the stellar nursery. This contrast reveals our seventh secret. The most massive stars are cosmic bullies, whose sheer power can shape and dominate their entire galactic neighborhood. These are the O-type stars, the largest, hottest, and most luminous stars in the universe, and their influence is anything but gentle. An O-type star is a true giant. It can be born with anywhere from 15 to over 100 times the mass of our sun. Because of this immense mass, the gravitational pressure at its core is beyond comprehension. This drives nuclear fusion at an absolutely ferocious rate. As a result, they are incredibly hot, with surface temperatures exceeding 30,000 degrees Celsius, making them shine with a brilliant blue-white light. They are staggeringly luminous, some of them shining with more than 1,000,000 times the brightness of our sun. A single O-type star can outshine an entire cluster of thousands of smaller sun-like stars. When one of these titans is born within a stellar nursery like the Orion Nebula, it immediately begins to wreak havoc on its surroundings. It unleashes a flood of high-energy ultraviolet radiation. This intense radiation is like a celestial blowtorch. It ionizes the surrounding hydrogen gas, stripping electrons from the atoms and causing the entire nebula to glow, creating the beautiful emission nebulae we can photograph. But this process, called photoevaporation, is also incredibly destructive. The radiation heats the gas in the cloud, causing it to boil away into space. The very pillars and dense filaments that are trying to collapse to form new, smaller stars are eroded and destroyed by the fierce light of their massive older sibling. The famous pillars of creation in the Eagle Nebula are a perfect example of this process. Majestic towers of gas and dust that are being slowly but inexorably vaporized by the radiation from a nearby cluster of massive young stars. In addition to this searing radiation, O-type stars produce immensely powerful stellar winds. These are streams of charged particles flowing away from the star's surface at speeds of thousands of kilometers per second. This wind is so powerful it acts like a cosmic snowplow, carving out huge empty bubbles in the molecular cloud, some of which can be hundreds of light years across. This wind can sweep away the gas reservoirs that smaller, still-forming protostars are trying to feed on, effectively starving them and stunting their growth, or even preventing them from forming altogether. The O-type star is a cosmic bully, clearing out its territory and dictating the fate of all its smaller neighbors. Its life is short, but spectacular and violent. After only a few million years, it will exhaust its fuel and explode as a supernova, sending one final devastating shockwave through the region. A shockwave that will both destroy what remains of its nursery and, in the grand cosmic cycle, trigger the formation of the next generation of stars. Feel that sense of awe and immense power. A brilliant blue-white light, a cleansing, forceful wind, a true titan whose brief, glorious life shapes the destiny of its corner of the galaxy. After the brief, violent life of a cosmic titan, or the quiet formation of a humbler star, the story is not yet over. In fact, a new chapter is just beginning. The birth of a star is almost always accompanied by the birth of its children. This brings us to our eighth secret, a truth that connects the grandest scales of the cosmos directly to us. Planets are born from the leftovers. As the great molecular cloud collapsed to form our sun, not all of the material made it into the central star. The law of conservation of angular momentum ensured that the infallen gas and dust flattened into a vast, spinning platter, a structure we call a protoplanetary disk. Picture it in your mind. A central, glowing protostar, and surrounding it, a disk of material stretching out for billions of kilometers, like a colossal, dusty vinyl record. This disk is the birthplace of worlds. It contained everything that would one day become Mercury, Venus, Earth, Mars, and all the other planets, moons, and asteroids in our solar system. We are, quite literally, made from the crumbs left over from the sun's formation. The process is one of almost unimaginable patience. Within this disk, which is initially about 99% gas and 1% dust, the magic of accretion begins. The dust grains are microscopic, smaller than the particles in a puff of smoke. But they are not idle. They orbit the young star, and in their slow, graceful dance, they occasionally bump into one another. In the cold outer regions of the disk, these grains are coated with sticky ices, frozen water, ammonia, methane. This frosty coating helps them to cling together when they collide. A tiny grain sticks to another, then another. It is a slow, gentle process of accumulation. Over thousands of years, these tiny agglomerations grow from dust grains into something more like pebbles. As they grow larger, their own gravity, however feeble, begins to help, attracting more dust and other pebbles. These pebbles drift inward toward the star, sweeping up more material as they go. Eventually, they form objects a kilometer or so in size. We call these planetesimals, the building blocks of planets. Now, gravity truly takes over. These planetesimals begin to collide and merge in a process called runaway accretion. The largest planetesimals grow the fastest, their gravitational influence snowballing as they sweep their orbits clean of smaller debris. This was a chaotic time in our early solar system. Millions of planetesimals were engaged in a cosmic demolition derby, a slow-motion dance of creation through collision. Over millions of years, these collisions built up the rocky cores of the terrestrial planets, including our own Earth. In the colder, outer reaches of the disk, where icy material was more plentiful, the planetary cores grew much larger, massive enough to attract and hold on to the vast amounts of hydrogen and helium gas that made up the bulk of the disk. This is how the gas giants, Jupiter and Saturn, were born. The entire process, from a dusty disk to a full-fledged solar system, takes about 10 to 100 million years. It is a slow, methodical construction project on a cosmic scale. The young star at the center presides over it all, its light illuminating the swirling dust lanes, its gravity conducting the orbital dance. So when you look at the planets in our night sky, remember that you are seeing the successful survivors of this long and patient process. You are seeing the beautiful, orderly result of a chaotic and dusty beginning. Visualize that vast spinning disk now, a cosmic potter's wheel. Imagine the slow, patient dance of particles, gently clumping together over millions and millions of years, building worlds in the quiet darkness, all while you drift peacefully, restfully into the quiet darkness of your own sleep. The young star, having gathered most of its mass and surrounded by its family of newborn planets, is not yet the calm, stable star we know our Sun to be today. It must first go through a turbulent adolescence. This brings us to our ninth secret. Before a star truly ignites, it must take its first great breath, a powerful wind that clears its nursery. This is known as the T Tauri phase. A T Tauri star is a star that has not yet initiated hydrogen fusion in its core. It is still contracting under its own gravity, and this contraction is its primary source of heat and light. These stars are young, erratic, and magnetically hyperactive. Their surfaces are modeled with enormous star spots, far larger and more numerous than the sunspots on our own sun. And they produce a stellar wind that is vastly more powerful and chaotic than our sun's gentle solar wind. This is the star's first great act of housecleaning. For millions of years, the newborn star has been shrouded in its natal cocoon, the dusty, gaseous remnants of the molecular cloud and its own accretion disk. While the star was forming, this material was its source of life. But now it is a veil that must be cast aside. The T Tauri wind is the force that does it. It is not a gentle breeze, but a fierce, gusting gale, blowing outward in all directions. It rushes through the young solar system, picking up the remaining wisps of hydrogen and helium gas and the fine-grained dust that was not incorporated into planets, and pushes it all out into interstellar space. This is a pivotal moment in the life of a solar system. This powerful wind effectively shuts down the planet-forming process, at least for the gas giants. Once the gas is gone, they can grow no larger. It is the star's way of saying, the kitchen is closed. This process is what determines the final architecture of a planetary system. The strength and duration of the T Tauri wind helps to sculpt the final arrangement of planets and clear the space between them. Imagine a thick, persistent fog filling a valley. And then, at the center, a light begins to glow, and with it comes a powerful swirling wind. The wind pushes and pushes, slowly at first, then with more and more force, until the fog begins to shred and dissipate. The light at the center grows clearer, more brilliant, as the last veils are torn away. This is what happens when a star enters its T Tauri phase. It is a moment of emergence, of revelation. It is the star announcing its presence to the galaxy, clearing its throat with a mighty gust before it settles down for a long and stable life. It is the transition from a shrouded, hidden object into a true, visible star. Allow yourself to feel that sense of clarity now. Imagine a powerful but gentle wind blowing through your mind, clearing away the fog of the day's thoughts, revealing the brilliant, peaceful stillness that lies within. A feeling of emergence, of clarity, and of a new and peaceful beginning. For all that we have described, there is a fundamental challenge to witnessing these events. Starbirth is a shy process. It happens deep inside vast, dark clouds of dust. This dust is completely opaque to the light our eyes can see. A molecular cloud is more opaque than a brick wall. If you were floating in space right next to a forming protostar, you would see nothing but blackness. The very cradle of creation is a place of impenetrable darkness, at least in visible light. So how do we know any of this is happening? This leads us to our 10th and perhaps most illuminating secret. We can peer through the veil by looking at the universe with different eyes, the eyes of infrared. Visible light is just one small slice of the full spectrum of light, or electromagnetic radiation. There are other forms of light, with longer wavelengths, that our eyes cannot detect. One of these is infrared light, which we feel as heat. A smoldering ember, a hot stove burner, even your own body, they all glow with invisible infrared light. And it turns out that protostars and stellar nurseries are fantastically bright in this part of the spectrum. The dust that makes these clouds so dark in visible light is also what makes them glow in infrared. The dust grains absorb the intense light and ultraviolet radiation from the young stars forming within them. This energy heats the dust grains, and they, in turn, radiate that heat away as infrared light. The entire cloud, which is black to our eyes, shines brilliantly when viewed with an infrared telescope. More importantly, infrared light has a longer wavelength than visible light, and this allows it to pass through the clouds of dust much more easily. The tiny dust grains that block visible light are too small to effectively block the longer infrared waves. It's like the difference between trying to stop a tiny pebble and trying to stop a large ocean wave. This is the key that unlocks the secrets of the stellar nursery. When we point an infrared telescope, like the Spitzer Space Telescope or the magnificent James Webb Space Telescope, at a dark patch of the Milky Way, the view is transformed. The darkness gives way to a tapestry of light. The dark cloud becomes a translucent, glowing curtain, and peppered within it, we can see the bright, warm points of light that are the protostars themselves, the very stars in the act of being born. We can see the shape of the jets they are firing, glowing in the infrared. We can see the structure of their protoplanetary disks, the warm dust shining like a cosmic halo. The James Webb Space Telescope in particular has revolutionized our view of these regions. Its incredible sensitivity and sharp vision in the infrared allow it to pierce through even the densest, dustiest cores, revealing details we have never seen before. It can see the faint glow of the smallest brown dwarfs, the complex structures carved by stellar winds, and even the shadows cast by forming planets within a disk. It has given us a front-row seat to the process of creation. Imagine now that you are putting on a special pair of glasses. The world around you is dark and quiet. But as you put on these glasses, the darkness is filled with a soft, warm glow. You can see the gentle heat radiating from objects around you. You can see through the walls of a dark room to the light beyond. This is the gift of infrared astronomy. It is a sense of revelation, of being able to see the unseen, of witnessing the secret, warm heart of creation, hidden away in the cold and quiet dark. Given the sheer amount of raw material available, you might think that turning a giant molecular cloud into stars would be a straightforward process. These clouds can contain hundreds of thousands or even millions of times the mass of our sun, enough to build entire galaxies of stars. And yet, this brings us to a surprising and counterintuitive 11th secret. Star formation is an incredibly inefficient process. The universe, it seems, is in no hurry and is quite profligate with its resources. When we observe a giant molecular cloud, a stellar nursery actively forming a young cluster of stars, we find that only a tiny fraction of the available gas actually ends up inside a star. The overall efficiency is shockingly low, typically only about 1 to 10%. That means for a cloud with enough gas to make 1,000 suns, it might only succeed in making a few dozen before the process shuts down. 90% or more of the precious star-forming gas is lost, blown away, and dispersed back into interstellar space. Why is creation so inefficient? It is because the very processes that trigger star formation are also the ones that destroy the nursery. As we've learned, the first massive O-type stars to form in a cluster are immensely powerful. Their intense ultraviolet radiation heats and evaporates the surrounding gas, a process we called photoevaporation. Their powerful stellar winds act like a snowplow, sweeping vast quantities of gas out of the cloud. The bipolar jets from smaller, still-forming stars also contribute, carving out cavities and pushing material away. And finally, after a few million years, these first massive stars explode as supernovae, sending a final, devastating shockwave through what remains of the cloud, blowing the rest of it to smithereens. The cloud is in a race against time. Gravity works slowly and patiently, trying to gather the gas into collapsing cores. But the feedback from the newborn stars is fast and violent. In most cases, the violence wins. The young stars effectively poison their own well, destroying their natal cloud before it has a chance to convert all of its mass into a new generation of stars. The process is self-regulating. Star formation continues until enough massive stars have formed to blow the cloud apart, at which point the process stops. Visualize a master sculptor who is given a colossal block of the finest marble. He sets to work, and from this enormous block, he carves a single, exquisite, perfect statue. The rest of the marble, 99% of it, is chipped away, becoming dust and rubble swept from the studio floor. To us, this might seem wasteful, but for the universe, it is simply the way of things. There is no scarcity of time or material. The gas that is blown away from one nursery will eventually cool, collect, and form a new molecular cloud, millions of years later in another part of the galaxy, ready to try again. It is a sense of cosmic patience, of an unhurried, grand cycle that is not concerned with efficiency, but with the simple, magnificent act of creation itself. Perhaps no single image has captured the human imagination quite like the one taken by the Hubble Space Telescope of the Eagle Nebula. It shows 3 colossal towers of gas and dust silhouetted against a glowing background of ionized gas. They were famously nicknamed the Pillars of Creation. They look solid, permanent, eternal. But this majestic image hides our 12th secret. The pillars of creation are also, simultaneously, pillars of destruction. They are caught in a beautiful, transient moment of being unmade. These pillars are a classic example of the destructive power of massive stars. They are essentially dense, resilient fingers of gas and dust that have survived, for a time, the intense onslaught of ultraviolet radiation from a cluster of hot, young O-type stars located just out of the frame above the pillars. The rest of the cloud around them has already been evaporated and blown away. The pillars exist only because they are dense enough to shield the gas behind them, creating these long, shadowy structures. They are like sandcastles on a beach, withstanding the first few waves of an incoming tide. But the tide is relentless. The surface of the pillars is constantly being photoevaporated. The intense radiation from the nearby stars is boiling away their outer layers, creating the glowing, hazy edges we see in the photographs. The pillars are shrinking. Astronomers estimate that they are losing mass at a prodigious rate. They are not eternal monuments. They are ephemeral like clouds of steam. And the destruction is not just coming from the outside. Deep within the tips of the pillars, hidden from our view in visible light, new stars are being born. Infrared images from telescopes like Hubble and James Webb pierce through the dust and reveal these stellar embryos, glowing like warm embers inside their cocoons. These newborn stars, once they ignite, will begin to hollow out the pillars from the inside with their own winds and jets. The pillars are being attacked from both without and within. They are the very site of creation, and yet they are being actively destroyed by the consequences of that creation. It is a perfect, poignant example of the cosmic cycle of life and death. In fact, there is some debate among astronomers as to whether the pillars are even still there. Light takes time to travel across space. We see the Eagle Nebula as it was about 7,000 years ago. Some evidence suggests that a supernova may have exploded in the vicinity a few thousand years ago. The blast wave from that explosion may have already swept through the nebula and completely destroyed the pillars. We won't know for sure for another 1,000 years or so, when the light from that event finally reaches us. It is a ghostly thought that we may be admiring a beautiful cosmic structure that, in reality, no longer exists. Visualize those majestic towers of gas and dust. See them not as solid stone, but as something delicate and transient, like morning mist rising from a valley. Feel their quiet, slow evaporation under the light of a rising sun. A feeling of profound and transient beauty, and a peaceful acceptance of the unstoppable, gentle cycle of cosmic change. The entire saga of starbirth, from a diffuse cloud to a shining sun, can be understood as a fundamental contest between two opposing forces. This brings us to the very heart of the physics involved, and to our 13th secret. Starbirth is a delicate balancing act, a cosmic tug-of-war between the persistent pull of gravity and the resilient push of pressure. On one side of the rope is gravity. Gravity is the great gatherer, the architect of the cosmos. It is a long-range force that is always attractive. Every particle of gas and every grain of dust in a molecular cloud feels a tiny gravitational tug from every other particle. Over vast distances and immense timescales, this gentle, cumulative pull is what coaxes the cloud to begin its slow collapse. Gravity wants to pull everything inward to crush it all down to a single point. On the other side of the rope is pressure. Pressure is the force of resistance. Initially, this is simply gas pressure. The atoms and molecules in the cloud are not stationary. They are constantly moving, whizzing around and bumping into each other. This random thermal motion creates an outward push, a pressure that supports the cloud against its own weight. For a cloud to begin to collapse, the inward pull of gravity must be stronger than this outward push of gas pressure. This only happens in the coldest, densest parts of the cloud, where the particles are moving more slowly and are packed more closely together. As the core of the cloud begins to collapse, this battle intensifies. As the gas is compressed, it heats up. The particles move faster, and the gas pressure increases, fighting back more strongly against the continuing collapse. If this were the only factor, the collapse might stall. But something else begins to happen. The protostar at the center becomes so hot and dense that it starts to glow, pouring out light. This light itself carries momentum and exerts a force. We call this radiation pressure. This is a second, powerful outward force pushing against gravity. It is the radiation pressure from our own sun that pushes on the tails of comets, causing them to point away from the sun. In the case of a forming massive star, the radiation pressure can become so intense that it can actually halt the inflow of new material, setting an upper limit on how massive a star can become. A star is finally, truly born when it achieves a state of perfect, stable equilibrium between these forces. When nuclear fusion ignites in its core, the energy released creates a tremendous, sustained outward pressure that precisely balances the inward crush of gravity. The star stops contracting. It finds its balance point. This state, called hydrostatic equilibrium, is what allows a star like our Sun to shine steadily for billions of years. It is a perfect truce in the cosmic tug-of-war. Feel those two opposing forces within your own body now as you breathe. the gentle inward pull of your inhale gathering energy and air, and the warm, expanding outward push of your exhale, releasing and letting go. A sense of perfect, delicate balance being achieved with each breath. A quiet equilibrium that leads you further and further into a state of profound peace. The inside of a molecular cloud is a dark, chaotic, and mysterious place. Trying to understand what is happening deep within the collapsing core of a protostar is like trying to understand the inner workings of a sealed engine while it is running. But astronomers are clever, and they have devised ingenious ways to probe these hidden regions. Our 14th secret reveals how we can do this, by listening for the slow, steady heartbeat of a protostar. Of course, we are not listening with our ears. Sound cannot travel through the vacuum of space. We are listening with light. The technique is wonderfully elegant. We find a bright, distant star that happens to be positioned directly behind the dark molecular cloud we want to study. The light from this background star travels through the cloud on its way to our telescopes on Earth. As the light passes through, the molecules within the cloud absorb some of it at very specific frequencies or colors. Each type of molecule, carbon monoxide, ammonia, water, has a unique spectral fingerprint, a barcode of colors that it absorbs. By looking at which colors are missing from the background starlight, we can determine exactly what the cloud is made of. But we can do even more. We can map the cloud's internal structure. Where the cloud is densest, like in the collapsing core around a protostar, more of the background starlight is blocked. The core creates a shadow. By carefully mapping the depth of this shadow, we can measure the density profile of the collapsing core with incredible precision. And this is where we can detect the heartbeat. The core is not just sitting there, it is rotating. As it spins, one side of the core is moving towards us, and the other side is moving away. This motion causes a tiny shift in the frequencies of the light, effect known as the Doppler shift. The light from the side moving towards us is shifted to slightly higher frequencies. It is blue shifted. The light from the side moving away is shifted to slightly lower frequencies. It is red shifted. By measuring this tiny split in the spectral lines, we can determine how fast the core is rotating. We can detect its spin. And as the core pulses and oscillates during its collapse, its rotation rate can change in a rhythmic way. We can, in essence, detect a slow, deep cosmic pulse, a heartbeat, taking perhaps thousands of years to complete a single beat. It is a profound connection to a living, developing cosmic entity. Imagine yourself now, in the vast silence of space, tuning in to this ancient rhythmic pulse, a slow, deep, and steady beat that underlies all of creation, a reassuring rhythm that tells you all is well. Let that cosmic heartbeat become your own, slowing down, growing deeper as you drift into a calm and dreamless sleep. These stellar nurseries, these great molecular clouds, are more than just the birthplaces of stars and planets. They are also vast, cold, and quiet laboratories where the universe conducts its most delicate and creative experiments. This brings us to our 15th secret. The dark, frigid hearts of these clouds are perfect cosmic chemistry labs where the very building blocks of life are assembled. The universe began with only the simplest elements, hydrogen, helium, and a tiny trace of lithium. Every other element on the periodic table, the carbon in your body, the oxygen you breathe, the silicon in the rocks beneath your feet, was forged in the nuclear furnaces of stars and scattered through space. These elements drift through the galaxy and eventually find their way into the next generation of molecular clouds. But they are mostly just individual, lonely atoms. For life to be possible, these atoms must join together to form complex molecules, and the molecular cloud is where this happens. The key ingredients for this chemistry are the cold, the dark, and the dust. The temperatures in these clouds can plummet to just 10 degrees above absolute zero, making them some of the coldest places in the known universe. At these frigid temperatures, atoms and molecules move very slowly, making it easier for them to stick together when they meet. The darkness is also crucial. The dense clouds shield their interiors from the harsh starlight and ultraviolet radiation of the galaxy, which would otherwise break apart any fragile molecules that might form. And then there is the dust. The tiny grains of silicate and carbon, no larger than smoke particles, act as cosmic meeting places. They are catalysts. In the vast emptiness of the cloud, two atoms meeting by chance is a rare event. But these dust grains provide a surface. An atom of oxygen might drift by and stick to the icy surface of a dust grain. Later, a hydrogen atom might land nearby, and then another. On the cold, stable surface of the grain, these atoms can skate around until they find each other and combine, forming a molecule of water, H2O. The grain becomes coated in a thick mantle of various ices: frozen water, carbon monoxide, methane, ammonia. This is just the beginning. The faint ultraviolet light that does penetrate the cloud can provide just enough energy to break some of these simple molecules apart, and their reactive fragments can then combine to form much more complex structures. Over millions of years, in this slow, patient, and protected environment, an astonishingly rich chemistry unfolds. Astronomers, using radio telescopes to detect the unique spectral fingerprints of these molecules, have identified over 200 different molecular species in interstellar clouds. We found simple alcohols, sugars like glycolaldehyde, and even the components of fats. Most profoundly, we have found the precursors to life itself. We have detected molecules like formamide, which can react to form all 4 of the nucleobases that make up RNA and DNA. And in meteorites that have fallen to Earth, pristine samples of the material from our own solar system's protoplanetary disk, we have found amino acids, the building blocks of proteins. The simplest amino acid, glycine, has even been detected in the gas surrounding comets and in star-forming regions. This means that the fundamental ingredients for life as we know it are not unique to Earth. They are being manufactured by the trillions of tons in these cold, dark clouds, long before planets even exist. They are then frozen into comets and asteroids, which act as cosmic delivery systems, seeding young planets with the very molecules needed to spark biology. Visualize those tiny frosted dust grains drifting in the silent dark. Imagine them as tiny, patient chemists slowly assembling the very ingredients of life, waiting for a world to call home.
It is a comforting thought that the universe is not sterile and empty, but is seeded with potential, waiting quietly in the dark, just as you are now waiting quietly for the gentle onset of sleep. Thus far, our journey has focused on the birth of stars within our own galaxy, the Milky Way. But the process of creation also plays out on a stage of almost unimaginable grandeur. To witness the most spectacular displays of starbirth, we must zoom out, expanding our view to encompass the cosmic dance of entire galaxies. This leads us to our 16th secret. When galaxies collide, the universe ignites with the fire of new stars. Galaxies are not static islands of stars. They are dynamic, moving under the mutual influence of gravity. And sometimes their paths cross. Our own Milky Way is on a collision course with our nearest large neighbor, the Andromeda Galaxy. In about 4.5 billion years, they will begin a slow, majestic process of merging that will last for hundreds of millions of years. But we do not have to wait to see what this looks like. We can look out into the universe and see other galaxies in every stage of this process. The antenna galaxies, for example, are a famous pair of spiral galaxies caught in the throes of a spectacular collision. When two galaxies collide, the individual stars within them rarely, if ever, hit each other. The space between stars is simply too vast. But the galaxy's enormous clouds of interstellar gas and dust are not so lucky. They are like giant diffuse sponges. As the galaxies merge, these vast gas clouds slam into each other, creating shock waves and compression on a galactic scale. The gravitational tides from the interaction pull out long, beautiful streamers of stars and gas, stretching for hundreds of thousands of light years. And within these compressed, chaotic regions, the conditions for star formation become perfect. The collision triggers a massive, galaxy-wide burst of star formation. We call these starburst galaxies. They are forming new stars at a rate that can be 10, 100, or even 1,000 times greater than the modest rate in our own Milky Way. Vast regions of the merging galaxies light up with the brilliant blue-white glow of millions of newborn O-type stars. The entire galaxy complex becomes a colossal stellar nursery. Infrared telescopes show these starburst galaxies glowing with ferocious intensity, as the dust in their star-forming regions is heated by the incredible number of young stars hidden within. These are the most prolific star factories in the modern universe. They are events of breathtaking scale and violence, but also of incredible creative power. They are a crucial part of galactic evolution, transforming two placid spiral galaxies into a new, larger, and often more chaotic elliptical galaxy, while using up a significant fraction of their gas reserves in a single brilliant flash of creation. Visualize now two majestic spinning spirals of light, slowly, silently drawing closer over eons. Imagine them passing through each other, their vast clouds of gas colliding, compressing, and igniting with the light of 1 billion newborn suns. It is a silent, cosmic firework display, a symphony of creation playing out on the largest possible stage. A reminder that even in the most chaotic encounters, the universe finds a way to create new light and new beauty. Let us now return from the grand scale of colliding galaxies to the quiet heart of a single molecular cloud. We have discussed the battle between gravity and pressure, but what is it that determines the winner? Why do some clouds, or some parts of a cloud, collapse to form stars, while others remain placid and diffuse for eons? The answer lies in our 17th secret, a cosmic tipping point known as the Jeans mass. This elegant physical concept was first worked out by the English astronomer Sir James Jeans in the early 20th century. He realized that for any cloud of gas, there is a critical mass that it must reach before its own self-gravity can overcome its internal gas pressure and trigger a collapse. This critical mass is the Jeans mass. If a cloud's mass is less than its Jeans mass, the gas pressure will win. The cloud will be stable or may even expand. If a cloud's mass is greater than its Jeans mass, gravity will win. The cloud will be unstable and will begin an irreversible process of collapse. The value of the Jeans mass depends on two key properties of the cloud: its temperature and its density. A hotter cloud has a higher Jeans mass. This makes sense because in a hotter cloud, the gas particles are moving faster, creating more outward pressure that gravity has to overcome. To make a hot cloud collapse, you need a lot more mass. A denser cloud, on the other hand, has a lower Jeans mass. This is because in a denser cloud, the particles are already closer together, so gravity has an easier job of pulling them all the way in.
This concept explains why star formation happens only in the specific environments of molecular clouds. These clouds are both extremely cold and relatively dense, which means their Jeans mass is low. A typical cloud might have a mass of 100,000 suns, while the Jeans mass for a star-forming clump within it might be only a few times the mass of the sun. This means the large cloud is not destined to collapse all at once into a single supermassive object. Instead, turbulence and shock waves create smaller, denser filaments and cores within the cloud. Whenever one of these fragments gets compressed to the point where its own mass exceeds its local Jeans mass, it is destined to collapse and form a star or a small group of stars. Imagine a scale perfectly and delicately balanced. On one side is the outward push of pressure. On the other is the inward pull of gravity. For a stable cloud, the scale is tipped in favor of pressure. But now imagine a slow, steady trickle of cosmic dust and gas being added to gravity's side. The scale slowly begins to move. With the addition of one final, decisive grain of dust, the scale tips over completely. The balance is broken, and a new process begins, a process that will not stop until a star is born. This is the Jeans mass. It is the universe's quiet, mathematical trigger for creation, the point of no return, a silent, invisible threshold that, once crossed, unleashes the power to build new worlds and new suns. Feel that sense of a gentle, inevitable tipping point in your own consciousness now, as the balance shifts from waking thought to the peaceful gravity of sleep. Our journey has revealed many ways we observe starbirth, from the visible light of glowing nebulae to the infrared light that pierces the dust. But there is another sense we can use, another window onto the cosmos that reveals processes hidden from all others. This is the realm of radio waves, and it brings us to our 18th secret. We can effectively listen to the process of starbirth. Radio astronomy opens up a completely different universe. The cold, dark gas in molecular clouds, which is invisible in optical light and only weakly glowing in the far infrared, is actually buzzing with faint radio signals. These signals are not intelligent communications, of course. They are the natural emissions from molecules as they rotate and vibrate in the frigid depths of space. Consider a molecule like carbon monoxide, which is abundant in these clouds. It is composed of a carbon atom and an oxygen atom, like a tiny dumbbell. This dumbbell is constantly spinning. Due to the laws of quantum mechanics, it can't spin at just any speed. It can only spin at specific, discrete energy levels. Occasionally, a spinning molecule will bump into another molecule and get knocked down to a lower energy, slower spinning state. When it does this, it releases the tiny bit of extra energy it had in the form of a radio wave with a very specific, characteristic frequency. A radio telescope is essentially a very large and sensitive radio receiver that we can tune to that exact frequency. When we do, the sky, which looks dark and empty to our eyes, lights up with the radio hum of all the carbon monoxide in a molecular cloud. This is an incredibly powerful tool. By mapping the strength of this radio signal, we can trace the structure of the vast cold gas clouds that are invisible to other telescopes. We can measure their size, their mass, and their density. And by measuring the tiny Doppler shifts in the radio frequency, we can map the motion within the cloud. We can see the turbulence. We can watch vast streams of gas flowing along filaments. We can measure the precise speed at which gas is spiraling inward onto a hidden protostar. It is like having cosmic weather radar for the stellar nursery. We are not just taking a picture, we are creating a dynamic, three-dimensional map of the entire creative process. Great observatories like the Atacama Large Millimeter Submillimeter Array, or ALMA, in the high desert of Chile, have revolutionized this field. ALMA is an array of dozens of large radio dishes working together as a single giant telescope. It can see the radio universe with the same sharpness of vision that the Hubble Space Telescope has for visible light. With ALMA, we can zoom in to the protoplanetary disks around young stars and see the gaps being cleared out by forming planets. We can watch the material being launched in stellar jets. We are, for the first time, truly witnessing the mechanics of creation in real time. Imagine now that the universe is filled with a symphony of faint cosmic whispers. Tune your own senses to one specific, gentle frequency, and in the quiet of your mind, hear the soft, steady hum of a stellar nursery, a cosmic lullaby being broadcast from across the vast, silent ocean of space, a soothing sound to guide you into your dreams. As a protostar collapses, it grows hotter and hotter.
The ultimate destiny of a true star is to become a nuclear furnace, powered by the fusion of hydrogen into helium. But this requires a core temperature of at least 10 million degrees. Before it reaches that formidable threshold, the protostar must pass an earlier, crucial milestone. This is our 19th secret. The very first spark of nuclear fire in a star is not from hydrogen, but from a heavier, rarer element called deuterium. Deuterium is an isotope of hydrogen. A normal hydrogen atom has a single proton in its nucleus. A deuterium atom has a proton and a neutron bound together. It is sometimes called heavy hydrogen. It is much rarer than normal hydrogen, making up only about one atom in every 6,500 hydrogen atoms in the universe. But it plays a starring role in the birth of stars. This is because deuterium will fuse together at a much lower temperature than regular hydrogen, only about 1 million degrees. As a collapsing cloud core gathers mass and becomes a protostar, its internal temperature steadily climbs. When the core reaches that 1 million degree mark, the deuterium atoms within it begin to fuse. Two deuterium nuclei can combine to form either a helium-3 nucleus or a tritium nucleus, releasing a burst of energy in the process. This is the first nuclear fire to be lit in the heart of the developing star. This stage of deuterium fusion is a critical turning point. The energy released by this fusion creates an outward pressure that pushes against the inward pull of gravity. For a time, it can actually halt the protostar's contraction. The protostar finds a temporary state of equilibrium, shining not from gravitational contraction alone, but from this first gentle nuclear simmer. This is what truly defines an object as a protostar, marking its transition from a simple, passively collapsing clump of gas. It has turned on its own internal power source for the first time. The amount of deuterium fuel is very limited, so this stage does not last long, perhaps only a few 100,000 years. But it is a vital phase. It stabilizes the young star, allowing it to peacefully accumulate more mass from its accretion disk. For low-mass stars and brown dwarfs, this deuterium-burning phase may be the only nuclear fusion they ever achieve. But for a star destined for greatness, like our Sun, it is just a prelude. It is the tinder that lights the main fire. Once the deuterium is exhausted, the contraction will resume. The core will heat up further until it finally reaches the 10 million degrees needed to ignite the long-lasting, brilliant fire of hydrogen fusion. Imagine a vast, dark furnace, slowly gathering its fuel. And then, deep within, a tiny pilot light flickers on. It is not the main blaze, not the roaring fire to come, but it is the first pulse of internally generated warmth, the first sign of life. A soft, steady glow that is a promise of the brilliant sun that will one day awaken. And so, we arrive at the end of our journey, and at our 20th and final secret. This is a secret that connects this grand cosmic story directly to you, lying here, now, in this quiet moment. It is the simple yet profound truth that the universe is not something separate from us. We are not merely observers of its grandeur. We are a part of it. We are part of it. We are made of stardust. The story we have told tonight of a vast molecular cloud, of turbulence and magnetic fields, of a collapsing core and a spinning disk, is our own story. It is the story of our sun's birth some 4.5 billion years ago. The planets of our solar system, including our Earth, were built from the leftover dust and gas in that protoplanetary disk. And the elements that made up that cloud, that dust, and that disk were themselves the legacy of an even more ancient story. The hydrogen in the water that fills your body was created in the Big Bang, 13.8 billion years ago. But almost every other element has a more dramatic origin. The carbon that forms the backbone of your DNA, the oxygen you are breathing with each slow, steady breath, the nitrogen in your muscles, the calcium in your bones, the iron in your blood that carries that oxygen to every cell, none of these were created in the Big Bang. They were forged, atom by atom, in the unimaginably hot and dense cores of massive stars that lived and died long before our sun was ever born. These ancient stars, in their final moments, exploded as supernovae, scattering their precious, newly made elements across the galaxy like a farmer sowing seeds. These elements mixed with the primordial hydrogen, enriching the interstellar gas. Over billions of years, this enriched gas gathered into new molecular clouds. One of those clouds was ours. It contained the ashes of countless long-dead stars. And when that cloud collapsed to form our sun and our Earth, it contained all the ingredients necessary for life.
Every atom in your body, with the exception of that primordial hydrogen, has been on a journey of almost unimaginable length. It was once part of a diffuse cloud, then was drawn into the heart of a star and cooked in a nuclear furnace. It was then violently ejected back into space, journeyed for millions of years across the void, became part of our solar nebula, coalesced to form our planet, and was eventually incorporated, through the food you eat and the air you breathe, into you. You are a direct physical embodiment of the life cycle of the stars. You carry the legacy of the cosmos within every cell. Feel that profound and peaceful connection now. Feel the immense history contained within your own quiet form. The atoms in your hand have journeyed across billions of years and trillions of kilometers to be here with you in this moment of rest. You are not small or separate. You belong to the universe, and the universe belongs to you. There is no separation. There is only a single, continuous, magnificent story of creation, and you are a part of it. A feeling of ultimate peace and of coming home. And so, our journey from a cold, dark cloud to a brilliant, life-giving star is complete. We have witnessed the gentle pull of gravity, the chaotic dance of turbulence, the quiet guidance of magnetic fields, and the slow, patient assembly of new worlds. This grand cycle of cosmic creation is mirrored, in its own way, in your own cycle of rest and renewal. Just as the star, after its tumultuous birth, finds a long, peaceful, and stable equilibrium, shining steadily for billions of years, so too can you now find your own point of perfect, peaceful rest. Let go of the last remnants of the day's turbulence. Feel the gentle gravity of sleep pull you down into a state of deep, nourishing calm. There is nothing left to do, nothing left to think. You are safe, you are at peace, and you are connected to the grand, quiet, beautiful rhythm of the cosmos. As you drift now into the final silent darkness of deep sleep, know that you are part of this story. You are stardust, dreaming, and the universe is dreaming with you. Sleep now, sleep well. And so, our cosmic lullaby comes to a gentle close. We have traveled together across unimaginable gulfs of space and time, journeying deep into the heart of a stellar nursery to witness one of the universe's most profound miracles. We began in the cold and the dark, in a vast, silent cloud of hydrogen and dust, a place of infinite potential, sleeping peacefully in the void. We felt the first patient whispers of gravity, the gentle, inexorable pull, drawing that silence and that darkness together. We watched as chaos gave way to order, as supersonic turbulence and the echoes of ancient supernovae sculpted the cloud, creating the dense, quiet cores from which new suns would be born. We saw the invisible hand of magnetic fields guiding the collapse, choreographing a celestial dance of unimaginable scale. From that collapse, a new light began to glow, a protostar, gathering its family of planets from the leftovers of its own creation. We saw it breathe its first powerful winds, clearing its cocoon to announce its arrival to the cosmos. And we learned that this epic journey, this transformation from a diffuse, formless cloud into a brilliant, life-giving star, is our own story. It is written in every atom of our being. This grand cycle of the cosmos is also your story tonight. The story of gathering your plight, of letting the swirling turbulence of the day settle like cosmic dust, of finding your own calm center. Just as the young star, its long and fitful journey of formation complete, finally achieves its perfect, delicate balance, its hydrostatic equilibrium, and settles onto the main sequence for billions of years of peaceful, steady light, so too do you now find your own perfect, peaceful equilibrium in the quiet harbor of sleep. The long journey into night is over. The work of the day is done. All is calm now. All is quiet. There is only the soft, steady rhythm of your breathing, a gentle tide pulling you out into a vast, peaceful ocean of dreams. You are home, here among the stars. You are made of their ancient light, and you share in their profound and silent peace. Rest now, stardust. Dream your cosmic dreams. Good night, friend. Sleep well. Good night.